Okay, the talk is on discovering transferable forensic features for the detection of CNN generating images. So it is based on this recently accepted ECCV paper that we had. So there is an archive link to that, but there is also a project page with code and stuff like this, which will be at the end of these slides. So this is joint work with Keshik, the PhD student, and Ngoc Chung and Prof. Naiman. Okay, what's the point of this? We want to detect, in principle, deepfake images. So we focus on this on images first. And so what are deepfake images? Deepfake images are images generated, not by a human using a camera, but by a CNN. And for this, trained detectors exist. And now there is a question in literature, actually, why do these trained detectors detect deepfakes? And the important point is, so with deepfake images, it's not like, explaining why there is a cat in an image. If there's something like there's a cat in an image, a human knows where the ground truth is. With deepfakes, the human does not know what actually makes a deepfake a deepfake. Yeah, it is not something like obviously visible. So, and we wanted to understand what does a neural network find in deepfake images. So what steps do we have to do here? So the first thing is we have to find relevant feature space channels in a trained deepfake detector. Yeah. And then you have to ask the question, how to validate these findings. How to validate that we actually got feature space channels from the neural network that are important for the detector, and it is not just noise coming from our explanation method. For this, we have to find a way, and we will discuss in a simple way. And then once you're validated that actually we found feature space channels which are important for the detection of deepfakes, we can analyze what do universal detectors for counterfeit images learn. So universal detector is in principle a detector which aims at detecting counterfeits from multiple generators. And once we know what they in principle learned, we can ask ourselves the question how to improve the current model. Okay, so how did we go about this? Well, we have trained universal counterfeit image detector models. One for ResNet 50 and one for an efficient net B0. And next, we have to discover relevant feature channels. Again, the problem is it's not an image of a cat or a dog, so a human cannot verify the findings. We have to resort to statistics to verify the findings. So what do we do? Well, we apply LRP, namely LRP beta 0. And the point of LRP is that it is an explanation which gives you a relevance score in principle for every intermediate neuron in a neural network. So for every feature map, we get an LRP score, which is indexed by the batch index, the channel, the height, and the width. But this is an LRP score in principle, including for channels and including for spatial positions. And we expect that the spatial positions, which are important for deepfakes, may vary from image to image. So we want to obtain actually a measure for a channel. So how do we do this? Well, we take the relevance scores and we take the positive parts. Because in LRP, the sign of the relevance has a meaning. So positive relevance is evidence for a prediction, negative relevance is evidence against a prediction. And since we are looking at what is important for finding a deepfake, we look only at the positive evidence here. And once we take the positive part, we aggregate it over the spatial positions to get a measure which depends on the channel and the particular image in the mini batch. And then we have to normalize that. The reason for normalizing is that we want to be able to compare different channels and different layers of a neural network. So what do? We take here in principle the absolute values of relevances and sum them over all channels, height and width. And then we get a statistic. And this is a statistic for channel and images, but we want to find the most important channels, so we average it over images. So it is not very difficult to do that. Actually, it's more difficult to get LLP beta done for ResNets and efficient nets, and this was stuff for which I had my own code. So this was in principle the idea why using these networks. So, and once we have a statistic for every channel computed over a number of deepfake images, then we can select the top K feature channels. And we selected 114 for ResNet and 27 for efficient net. And that's roughly something in the order of 0.5% of the total number of channels for these networks. The ResNet has many more channels. The efficient net is much more slimmer. That's why the number of channels is here. That's it for both, roughly 0.5%. Okay. We found top K feature channels, but of course, these feature channels might not be actually important for the neural network, because all these explanation methods, they are just an approximation for explaining the decision. So we need somehow to validate the discovered top K feature channels. And we cannot eyeball, so what do we do? Well, we do the following. We measure an accuracy drop when performing the dropout of the found top K relevant feature channels. But we need also baseline. So we also measure the accuracy drop when performing a dropout on K randomly selected feature channels. But a random selection is random, so we perform this 5 times and we average these accuracies that we obtain. Because for random dropouts, how do you choose? So we perform it a few times and average this. And finally, we perform also dropout of the bottom K relevant feature channels and we compare the accuracies. So what can we see? Let's consider this table. I make it a bit bigger. I hope you see it well enough. So here is in principle the ResNet 50, and here are several in principle fake image generators, deepfake generators. And now we do the following. Baseline is the neural network detection performance as it is. This is the average precision measure on positive and negative. This is in principle the performance on the real images, and this is performance on the deepfake images. So there are always 3 columns. This is average precision. This is real image performance, GAN performance. Baseline is a neural network as it is, and the neural network was trained on ProGAN, so you have very, very good detection here. And then we do a dropout of the top K channels. This means this 114 channels found by LRP, and we measure the detection performance. And what we see, for example, on the program, average precision goes from 100 to 70 down. The performance on the real images still stays quite good, but when you remove those channels with the highest relevance, then the GAN detection performance drops terribly. From 100 to, I don't know, 3 something. And if you do this on some other deepfake generators, we see the same. StyleGAN 2, little drop on real, a heavy drop on the generated one. And same for all others. So we see if we mask dropout the LRP found channels, we see a very high decrease in detection accuracy on the generated images. What happens when we drop random channels? Well, we obtain a small drop, but the drop is much lower compared to dropping the top K found channels. And you see this across all kind of GAN generated images. And the same for efficient net. Efficient net is a neural network that has it's a slim architecture. Slim in the sense it's not a wide network. So 0.5% is 27 channels. We drop them. On ProGAN, you fail everything. On StyleGAN, it drops from 85 to 7 and so on and so on. Random K is much lower, the drop everywhere. So what's the point of this? We see that the top K feature maps found by LRP seems to be really important for the detection of GAN-generated deepfake images. There are people who say, you shouldn't use certain methods when they fail sanity checks. but there is a problem with sanity checks, and we are preparing a research paper where we mathematically deal with that. But it's clear, yeah, that this thing seems to work. Okay, let's go to next. So once we know that the discovered feature channels are really important for the network, let's visualize them. And so how to visualize them? Well, we choose the channels belonging to the top K feature maps. And then we find for a certain deepfake image those spatial locations with the maximum relevance of the channel. Yeah. And this is a channel in a feature space, but we can back project that in principle to the input space, find a corresponding location input space. And what we see when we see these top patches, they have one property. They look very colorful. Yeah. And then you can ask yourself, is color an important feature or texture as we actually assumed? Yeah. So what can we do in principle to see whether really color is important or not? Because we found the feature channels. Yeah. We found the spatial patches for these feature channels that are they have the maximum relevance, and not the maximum activation, maximum relevance. Maximum LFP relevance. Okay, so in principle, we can measure the detector accuracy across GANs with color ablated deepfakes. Yeah, so we take deepfake images and we just grayscale them and see what happens. Okay, so this is ProGAN here on the rightmost. I want to have something like a vocal screen show click, but again, I'm not using use Windows, so I wish to have a show click to put in principle here something. Never mind. So the deepfake detector was trained on ProGAN. And when I do grayscale ablation, I see a very small performance drop. Yeah. So here the same. Yeah. But when I use grayscaled here, when I use grayscale counterfeits and I use a GAN on which the detector was not trained, I see a very high score drop. Yeah, something like 98.9% for StyleGAN generated images, 99% for StyleGAN 1 generated images, 92% for BigGAN images, and 99.6% for CycleGAN images. So what do we see here in principle when we look at that? On the domain where the universal detector was trained, ProGAN, when we use grayscaled images, there is a very moderate performance drop. But on images from other GANs not used in the training of a generator, we see a very, very heavy score drop. Yeah, this is something which is apparent. So what does it see? And this is in principle the same thing here with another network, with the efficient net. Yeah, you see again in principle the same heavy drop. So color seems to be important for deepfakes when you go across domains. Yeah, that's in principle the important thing. But within the domain, within the actual domain where you're trained, grayscaling doesn't lead to a drop. That means that within the domain you're trained, seemingly the network is not relying on color, but also on other cues. Okay, so what did we do here? We did the same drop analysis, now with another fake image data set. Yeah, a second fake image data set, and we still see this substantial drop. So this was in principle a data set used for BigGAN training. Now, on the BigGAN, you do grayscaling, you see no drop, as here. But on ProGAN, StyleGAN, and all the others, you see a heavy drop. So it's not limited to one data set. Okay. One can look at this in principle statistically. Yeah. So one can also look at not only at relevances, but at forward pass activation statistics. Yeah, for original versus grayscaled images for the relevant channels. And what we see here is that for many of those relevant channels, the forward pass activations for grayscaled images, as in orange, are much lower than for the blue ones. Okay. So we've learned something. We've learned in principle that deepfake detectors, when you use them across generators, they seem to use color askew. And when you remove the color, they seem to fail. So how can we improve the cross-scan detector performance? Well, the idea is quite simple, right? We train with a certain percentage of grayscale counterfeits. And now we did the same experiment. So we trained a universal detector on ProGAN. Now with 50% grayscale images, there is now no drop anymore on within the same domain. And all the other domains where you had some like 90%, 70% drops, we have drop in performance of 2.7%, 5.8%, 8.5%, 0.9%. Yeah, so the drop is now much less pronounced. So we see indeed, how should I say, an improvement. That's all. This is in principle the end of the talk. There is one thing that I can also show you. Can we ablate channels in the generator to fool the detector? And what I did in principle, I took one of these GAN architectures, and in principle, they just use, convolution, batch norm, the same thing, ReLUs. So you can just run LRP through this. And I backpropagated the LRP scores from the detector into the image, then into the GAN generator. And then I can ablate things in the GAN. And this is what we did. And when you ablate channels in the GAN, also the detector performance drops. But this is not a very good idea for practice, because the GAN generator with ablated channels creates you very weird looking images. Yeah, then indeed the performance drops. Yeah, so 5% LRP high scoring channels versus 5% random channels. Yeah, if I ablate the 5% LRP high scoring channels in the generator, performance drops, but you get not nice looking images anymore. Yeah, and by the way, here's also a study where we did this evaluation on the channel ablation in a discriminator. Yeah, what happens if you ablate more and more channels? Yeah, and then you see typically then a drop. So that's all for the talk.